All right, before we get started, guys, huge die-hard Celtics fan, and we lost the finals today. It's all good though. Still a young team. Warriors are just stacked. They got Klay Thompson, Steph Curry. That was just crazy, man. But you know what? It's kind of crazier as we were 11th in the East at one point. And look at this tweet from Jaylen Brown back in January, saying the energy's about to shift, and that was the craziest thing that happened throughout the whole season. You know, we finished Eastern Conference champions, but just wasn't enough. But anyways, let's go ahead and get started. It is what it is. So let's use the principle of minimum potential energy developed in section 2.6, right, for the spring problems. Plot the total potential energy for variations in the displacement of the free end of the spring to determine the minimum potential energy. So, and we have to observe that the displacement that yields the minimum potential energy also yields the stable equilibrium position. So let's go. All right, so I'm gonna go ahead and explain it, assuming you didn't watch the other video. But overall, for potential energy problems, this is the overall goal. So the total potential energy is equal to the internal strain energy plus the potential energy by the external forces. So in this case, the external force is this weight right here, right? The mass is 400, so the weight you multiply by 9.81. That's gonna give you, let's see, 3924 newtons. All right, that looks right. Cool. So yeah, this is the overall goal, right? We got to get U, the internal strain energy of the spring of the system, and then the potential energy of the force being applied to the system. So let's go ahead and do that. If you didn't watch the other videos, right, this is, they don't mention it here, but this is a linear spring. You always assume it's linear if they don't tell you otherwise. They'll say it's non-linear if it's not, obviously, right? But the thing is about the thing for a linear spring is, so the load displacement curve looks something like this. This is X, right? And this is force. It varies linearly, okay? And that slope is K. So this equation right here, force is equal to Kx, right? Negative just determines the sign, so it's really just Kx. So when you take the, so this is the load displacement curve. So if you take the integral of this curve right here, in this case it's a nice straight line with respect to x, you will get kx squared over 2, right? That's just integration. And the area under the curve, that is energy. So that is U right there, okay? So let's go ahead and make that note. U is equal to 1/2 kx squared. If it was nonlinear, they'll give you the relationship. I think in problem 220 they had mentioned force is equal to like k delta squared. In that case, right, it's no longer kx, delta is squared, so that's a nonlinear spring, but that's another problem. Potential energy due to the external force, that is just negative Fx, right? It's always opposite to the internal strain energy. There's theory behind it. I'm not going to cover it, but you should probably read the book if you want to know why it's negative, but just take my word for it. So that means this is the ultimate goal, finding pi of p, which is a total potential energy, it being k half kx squared minus Fx. Okay, so we have our K, right? They give us 2,000. There's no point in converting. I have newtons, millimeters. There's no point in converting to meters. Like just FYI, but I guess you could do that if you want, but I'm not going to. Pi p is equal to 2,000 times half. That is 1,000 x squared, right? I just plugged in K, multiplied it by half, minus 3924x. That's the total potential energy equation for this specific problem. Again, this will change depending on your stiffness and your weight, obviously, right? But cool. So the problem says find the minimum potential energy and what's the displacement for that value, pretty much. So the way you do that is you take just like in calculus, right? You set the derivative equal to 0, and you solve for x pretty much. Right here, just by looking at the equation, it's a positive x squared, right? So it's a parabola, so it's gonna open up like this. So I know if we take the derivative, set it equal to 0, you're gonna get the minimum value for potential energy. So that's pretty much it. Let's go ahead and do that. So the partial derivative with respect to x, you set it equal to 0. And then that equation is 2000x, right? Take the derivative, minus 3924. Solve for x, you will get x is equal to 1.962 millimeters. So what this is saying is, with this stiffness and when you apply this force, this system will be in equilibrium, and that distance that it displaces going down, it's going to be 1.962 millimeters. Okay, that's pretty much all it's saying, and we just have to verify that that is indeed the minimum potential energy. When you start plotting it, you'll see what I mean right now. So now that we have the x, to find the value of the minimum potential energy, you just plug in this x into the original equation, not the delta pi p, whatever. So let's go ahead and do that. Pi p. I can't believe the Celtics lost. Shit. Still on me, but it is what it is. Maybe next year. Right, you just plug in 1,000, 1.962 squared minus 3924 times 1.962. Okay, that value is going to be pi p of 1962. Again, we use this equation. That, if you do the math, you will get negative 3849.44. And this is newtons times millimeters. So this is the answer. This is pretty much saying when the system's in equilibrium, right, when it extends 1.962 millimeters, the minimum potential energy will be negative 3,849. We could go ahead and plot that. You could make other test points, right? We have to prove that this is indeed the lowest, but it's pretty easy. What I like to do in these problems, look, this is how the graph is gonna look. So let's try to make it nice, right? Like that. Okay. So your x is 1.962, right? This is displacement, and this is potential energy, total potential energy. So 1.962, let's assume it's right here, 1.962. And that value of potential energy is negative 38, I'm just gonna put 49, whatever, right? Newtons millimeter. So that point's right here, right? And you plot it. Now, instead of just choosing random points for x, I like to make my life easier and just see where it's gonna cross the x-axis, because I already know it's a parabola, right? I told you it's gonna open up, and the point that we find, which was this one, is the minimum point. So the parabola is gonna open up something like that. I just want to see where it crosses the x-axis, and I'm fine with that. So just 3 points in total, this one and 2 more. So to do that, all you got to do is set your original potential energy equation equal to 0. So not the derivative, the original one. So pi p is equal to 0, and that is 1,000x squared minus 3924x. Factor out an x, right? X times 1,000 minus 1,000x. 1,000x minus 3924. Solve for your x's. X is equal to 0, right? And then x will also be equal to 3.924 millimeters. So that means that this parabola is going to hit the x-axis at 0, 0, right? And 0, 3.924 for x. So that's probably, oh look, it's a perfect halfway, right? This is right between these two, right in the center. So 3.924, and it's gonna hit right there. So that's pretty much your answer. Just draw it up, right? Make it look nice. I didn't make it look nice, but whatever. You get the idea. And that pretty much solves the problem, right? It says observe that the displacement that yields the minimum potential energy, so that displacement's 1.962, also yields the stable equilibrium position, right? We determined that when you apply that force, that's how much it's going to displace, and we saw that that is indeed the minimum potential energy right there. So cool, this problem's done. There you go. I'm gonna go ahead and get started with section D, or part D of the problem. So same thing, right? We're looking for pi p, and I'm not going to explain how to get it again, right? But it's 1/2 kx squared minus f of x. This is your omega, this is your u. All right, so same thing, right? The load displacement curve is a nice linear spring. They give us our k values and our force. Actually, the force is, hold on, let me pull it up real quick. That force is 981 newtons. Okay, so pi p is equal to 400 times half. That is 200 x squared minus 981 for your force, right? Newtons. Not newtons, x. And this equation will be in newtons times millimeter. Okay. So this is our equation, right? Same thing. This is step 1. So step 2, set it equal to 0, the derivative, right? That's going to tell us where, because again, this parabola is positive, so it's going to open upward like that, going up. And that derivative, when you set it equal to 0, it's going to give us the displacement that it shifts down. And you'll see later, obviously, you saw in the other problem, that gives us our minimum potential energy. So set it equal to 0, right? Delta pi p, partial x, my bad, whatever. Set it equal to 0, and that is 400x minus 981. So for your x value, x is equal to, let's see. Sorry, give me a second. 2.45 millimeters. So that means, again, I'll explain it one more time, that when you apply this force, this weight here on this spring, it's going to displace 2.45 millimeters. And we have to prove that that displacement will yield the minimum potential energy. And we saw in the other problem we did, right? Goddamn Celtics. Cool, so now that we have this x value, we want to find the value of that potential energy, right? So we just plug in this x into here, and that's going to give us pi p equals to something newtons times millimeter. So step 3, pi p of 2.45 millimeters. Put the units. It's 2.45 squared minus 981, 2.45. Solve for pi p. That's going to give us some minimum potential energy of negative 1202.95 Newton millimeter. So again, that means when it shifts down 2.45 millimeters, that potential energy will be the lowest, and it is negative 1202.95. So now that we have that, again, we just want to find more test points. This is what the graph is going to look like. Let me get some lead. Okay, it's negative 1202, right, for pi p. This is pi p. and this is x. Okay, and at the x equals 2.45, so let's put it right here, 2.45, your potential energy is negative 1203. I'm just rounding it up, and that point's right there. Now, again, I know it's a parabola, it's going to open up, so I just want to see where it crosses the x-axis. So set the equation, this one right here, equal to 0. Step 4, pi p is equal to 0, and that is equal to just the equation, 200x squared minus 981x. 0 is equal to x times 200x minus 981. That means x is equal to 0, and x is also equal to, what is this right here? It's usually, I didn't do the math, I'll be honest, but it's usually half of that. It should be half of that. Let me pull it up. I got my calculator right here. 981 divided by 200, 4.905. So, yep, it's right here, probably halfway. So that just tells me it's going to cross at 0, 0, so it's right here, and then 4.9050, so right here. So yeah, that's pretty much the answer. Just draw the parabola. That's how it's going to go. Something like that. And you should be good. Like I said, this is the minimum potential energy, so yes, it's verified. Observe that the displacement that yields the minimum potential energy, which is 2.45, also yields the stable equilibrium position. So yep, that's the answer. Hopefully the Celtics win next year, but I guess we'll see, right? But yep.